The purpose of this video is to review some of the open source programming languages that can be used to perform machine learning tasks. Open source languages are not only great because they're free for you to use, but they also enable you to freely share your work with the rest of the world. I will cover the two incumbents, R and Python, the two forces in the so-called data science wars. When I started doing grad work in data science a half dozen years ago, we did everything exclusively in R in every class. When I look at data science curriculums today, some are still all in R, but some now include both R and Python, and some even use only Python. Octave is often called the open source MATLAB, and MATLAB was very influential to the development of languages like Python. For example, NumPy adds MATLAB-like math functionality to Python. They both use the same underlying code for efficient linear algebra computation. And, as its name hints, the Python matplotlib package emulates MATLAB's plotting capabilities. Octave users find Julia's syntax to be familiar because it strongly resembles MATLAB. The new kid on the block, Julia, is much talked about as a possible replacement for R and Python in the near future. Scala is also a relatively new language, so much so that I found its packages for machine learning to be rather immature. Therefore, much of my demonstrations will be with distributed Scala, which is better known as Spark. Since I will review both Spark and Python, I thought it would be wise to also include PySpark, which is an API that allows you to interact with Spark's framework via Python code. Since the open source community uses version number 1.0 as a major milestone to indicate that a particular software package is considered reliable enough for general release, I'll show when each of our languages released their 1.0 version. Python 1.0 came out in January of 1994, and then Octave 1.0 was released the following month. However, it's important to remember that Octave is based on the much older MATLAB, which had its 1.0 release a whole decade earlier. The R project began in 1992, but didn't reach maturity until the turn of the century. As of this recording, Scala has been stable now for 15 years. Spark hit 1.0 in 2014, and Julia just recently reached the milestone. So in terms of stable open source programming, we'll be looking at a 25-year span of time. One way to compare the languages is to see how they're categorized. From day one, R has always been used for statistical computing, and its governing body is still called the R Foundation for Statistical Computing, with its headquarters located at the Institute for Statistics and Mathematics. Its mother tongue, MATLAB, is nicknamed the language of engineering, and Octave continues this tradition, advertising itself as a scientific programming language for numerical computation. The other four are all considered to be general-purpose programming languages. As the old saying goes, Python is the second best language for everything, which is actually a good compliment because Python can be used to handle everything from data mining to website construction to running embedded systems. In fact, Internet security monitoring companies report that at least 25% of all cyber attacks come from software written in Python. That's something you'll never hear about in R. When Julia was first announced, its manifesto declared that we want something as usable for general programming as Python, as easy for statistics as R, as natural for string processing as Perl, as powerful for linear algebra as MATLAB, and as good at gluing programs together as the shell. Scala is a functional and object-oriented language that can be used for many purposes. and Spark was designed as a general-purpose framework. Looking at the originally stated purpose for each language also provides insights into its development. R and Octave were both created as courseware for college classes. R for statistics and Octave for chemical engineering. For a long time, this was Python's main catchphrase. Its original author said that the development of system admin utilities in C was taking too long, and doing these in the Bourne shell wouldn't work for a variety of reasons. So there was a need for a language that could bridge the gap. The creators of Julia were frustrated because they had to switch back and forth between different languages for different tasks. So they wanted to create one language that could be used for many purposes. Scala was created to be a better Java. And if you've ever struggled to use Java with all of its boilerplates and quirks, then you'll love Scala. Spark was created to be a better Hadoop, especially to deal with Hadoop's need to persist intermediate data to disk after each task completes, which made it best for slow batch processing. Another good way to compare languages is by looking at their built-in data structures, their native containers. R is vector-based. A matrix is a two-dimensional vector. An array is a vector with 3 or more dimensions. Lists are vectors with elements of varying types, and a data frame is a list of multiple named vectors. The data frame object originated in the S language, and I highlight it here because machine learning practitioners almost always prefer to use this data structure, which is similar to a table in a relational database. Octave is based on MATLAB, and the name MATLAB is short for Matrix Laboratory. Octave is largely built around matrices and n-dimensional arrays because MATLAB started life as an interactive environment for performing two-dimensional matrix algebra and computation. Python consists of a small core language and a huge set of modules to extend it. Very little useful statistical programming can be done without additional modules. For example, NumPy is a library which adds MATLAB-like support for multidimensional arrays and matrices. And the Pandas library was created to mimic R's data frame functionality. In Julia, groups of related items are stored in arrays, tuples, or dictionaries. Arrays can be used for storing vectors and matrices. Spark's Scala and Python APIs share most of the same data structures, including a built-in data frame object. One question that I hear a lot is, why was R named only with a single letter? Two programming languages were created in the 1960s at the University of Cambridge in England. CPL, the Cambridge Programming Language, and BCPL, a simpler language which stood for Basic CPL. Within the next decade, 3 languages were created at Bell Labs, the research arm of Alexander Graham Bell's telephone company. B was essentially BCPL, stripped of any component they could do without to make it fit within the memory of a computer from 1969. Since a significant portion of BCPL was stripped away, they simply named the new language B. The author of B was also an author of C, and he chose its name simply because it was the next letter after B. When they created a statistical programming language, Bell Labs wanted to name it Statistical Analysis System, but that name was already taken by SAS. So the name S was chosen to continue the Bell Labs one-letter naming tradition. R was created at the University of Auckland as an implementation of the S programming language. So, as a play on the name S, and in honor of the two authors' first names, Ross and Robert, the language was named R. The author of Python was a fan of the British TV show Monty Python's Flying Circus, so he named his language after the Monty Python comedy troupe. The authors of Spark had first created a cluster computing manager named Mesos, and they wanted to demonstrate how easy it was to build a new framework on top of Mesos, so they built Spark to spark an interest in Mesos, which is, oddly enough, nowhere near as popular as Spark is today. The name Scala stands for Scalable Language because it was designed to grow with the demands of its users, from writing small interpreted scripts to building large compiled applications. Julia was named after Julia Roberts from Pretty Woman. Well, not really. That's just a rumor. When asked why it was named Julia, one of the authors said, "That's everybody's favorite question. There's no good reason, really. It just seemed like a pretty name." Octave was named in honor of one of the author's former professors, Octave Levenspiel, who wrote a popular textbook about chemical reaction engineering, and who was also well known for his ability to quickly do back-of-the-envelope calculations, like these calculations on the book's cover. It was hoped that the language would make it possible for people to do more ambitious computations just as easily. Let's look at each language's country of origin. Spark, Octave, and Julia all originated in the US. Python came from the Netherlands, Scala started in Switzerland, and R got its start down in New Zealand. Most books about programming begin by having you create a Hello World program, which simply prints Hello World to the screen, so that you can become familiar with the basic tool chain required to build and run a program. Linear regression analysis has been called the hello world of machine learning because it's widely used and easy to understand. I'm going to use it so that we can focus on language specifics rather than on machine learning topics like model selection and overfitting. I used a small CSV file which contains average height and weight values for a group of American women from 1975. When I created a scatter plot of my data points using R, you can see a fairly linear relationship. When I fit a straight line to the data, you can see that it lines up pretty well, except for near the middle and at the ends. This plot suggests that we might be able to improve our predictions by using a curved line with one bend in it. Polynomial regression allows us to predict a dependent variable from one or more independent variables where the form of the relationship is an nth degree polynomial. In our case here, a second degree polynomial produces a quadratic equation whose line fits all of our points more closely. Since we'll be using the ordinary least squares method, we'll use the r squared value to ensure that our languages produce similar models, where r squared equals 1 minus the residual sum of squares over the total sum of squares. One of the points of confusion for people new to open source programming is the various choices of IDEs and notebooks which are available. I used a combination of 6 different interfaces during my language research, and I'll quickly describe them now. Back in the day when we were working with languages that could use an interpreter instead of a compiler, we had a simple language shell, like this R console, which was an interactive environment that took single user inputs, evaluated them, and returned their result. Then, integrated development environments became available. Pictured here is the RStudio desktop client, which is the most popular environment for working with R, and the pinnacle of all machine learning IDEs. From this interface, I not only have access to the R console, but also to a script editor and several panes with useful data, like my global variables, connections, files, packages, plots, and a help system. Python programmers have a similar IDE named Spider, and it compares favorably to RStudio. Julia has an IDE named Juno, which is an extension of the Atom text editor. I found Juno to be a significant drop-off in maturity compared to RStudio and Spider. Another useful option, instead of IDE clients, are browser-based interactive notebooks, which contain a series of cells with executable code, visualizations, and prose descriptions. The king of notebooks is Jupyter, seen here. Jupyter is language agnostic, and its name is a reference to the core programming languages it supports, which are Julia, Python, and R. Even though you can use Jupyter with over 100 languages, it's most prominently used by Python programmers. You can use Apache Zeppelin with many languages, but its built-in Spark integration makes it especially useful for distributed programming with Scala or Python. Zeppelin is similar to Jupyter, but it also includes limited built-in plotting functionality. Here, you can see that I could visualize my original dataset as a scatter plot, but I could not draw a regression line on top of it. Databricks is a company founded by the creators of Spark to enable cloud-based Spark usage. The Databricks notebook is similar to Zeppelin and also includes limited built-in plotting. So I used 3 different IDEs and 3 different notebooks, which all improved my productivity and the reproducibility of my work. Now we'll start to look at some simple code samples. When we look at code for each language that can read our CSV file into a data frame, the first thing that you'll notice is that since Python, Octave, and Julia do not contain built-in data frame objects, we have to import packages to be able to use data frame structures with these languages. Another thing to note is that the Scala and Python APIs for Spark assume that our CSV does not contain a header row and that we want our column data types to default to strings. On the other hand, R, Python, Octave, and Julia all make the better assumptions about typical CSV files, so we do not need to override any of their defaults. Now we'll take a closer look to see how linear models are fit and what their summaries look like. R uses the formula notation which originated in S to describe the model to be fit, where the tilde symbol separates the dependent variable on the left from the independent variables on the right. When we execute the summary function on our model object, we get an explanation of the results. You may recall that the equation for a straight line is y equals mx plus b, where m is the slope and b is the y-intercept. You see that our equation predicts a weight as being 3.45 times the height minus an adjustment constant of 87.51667. The first observation in our CSV file has 58 inches for height and 115 pounds for weight. When we plug 58 into our prediction equation, we get about 112.5 pounds, which is fairly close to the actual value of 115. Our 0.991 R-squared value indicates that our model accounts for 99.1% of the variance in weights. When we perform a similar linear regression with Python, we receive similar intercept, coefficient, and R-squared values. We'll compare Python to PySpark to see how different their code is. We get similar results, but we definitely had to work harder in Spark. Comparing the Python and Scala APIs for Spark, we see both similar code and results. So if you can use Python with Spark, it won't be difficult for you to use Scala with Spark, or vice versa. Now let's see how Python compares to Julia and Octave. The steps and results are similar, just the syntax varies a little. The older Octave syntax definitely differs more from Python, even though the results are similar. When we look at all of the model fitting code together, you can see that R, Python, and Julia can all use the S formula notation to describe a model. And even though we are only using one independent variable, Octave and the Spark APIs insist that we wrap it in a vector. Now we'll look at the code used to visualize our linear model. You can see that we have more variation on this step. R and Octave have built-in visualization libraries that we can use. R and Python will automatically use our fitted model object to draw a regression line. But with the others, we first have to use various methods to generate predicted weights using our model. The amount of code used to draw the scatter plot and regression line varies greatly from among the languages. The result is 6 similar plots, but only half of them, R, Python, and Scala, automatically label the axes. Next, we'll quickly go over the steps to improve our prediction by using a regression with a quadratic term. Let's take a look at some of the interesting variations. I initially used Julia's polyfit function, but it only gave me the coefficients and intercept. I couldn't display the R-squared value. The authors of Julia knew it would be a long time before their language was mature, so they enabled you to call R, Python, C, and Fortran functions from within a Julia script. I decided to import the rcall package so that I can call R functions. You can see I used the same code in Julia that I used in R. Like before, Octave and the Spark APIs forced me to put my independent variables into a vector. Spark has a function to expand our height variable into a polynomial, but as you can see, it's a lot more involved than the other languages where we can simply raise height to the second power by using a built-in exponential operator. The results of the polynomial regression were similar for all 6 languages, so I'll just show one example summary here. By applying the coefficients and the intercept, our quadratic equation looks like this. And when we plug in 58 inches for height, we get a predicted weight that's only about an ounce more than the actual value of 115 pounds. So bending the line made our model fit better, and our R-squared value increased to a nearly perfect 1. All of the languages created nice default plots. Looking at the code, we see that only R could directly use our fitted model object to draw the curve. And again, the default plots were all sufficient to get our point across. I'll end now with a few conclusions. Here's something fun. I took all of the code that I displayed throughout this video, removed the blank lines, and used the same small font for each language. As you may have suspected, R has the least amount of code. OLS regression is one of the most common varieties of statistical analyses, and R is a statistical programming language, so it only makes sense that R has a linear modeling function and a data frame structure built right into its codebase. Also, the Spark examples were rather verbose compared to the non-distributed languages. R is a one-stop shop for data science and machine learning. It was written by statisticians for statisticians, and its tidyverse collection of packages is great for data wrangling. If you don't have a lot of programming experience, Python is a great first language to learn. It has a small learning curve and a design philosophy that emphasizes code readability. Plus, Python is a language that will serve you well in other aspects of your career too, as it is good for more than just machine learning. My ultimate recommendation is to learn both of them. In my neighborhood, we have a Walmart next door to a Target. I prefer Target and can usually find everything I need there 90% of the time. For the other 10%, I can get the items at Walmart. You can use R and Python in the same way. Use your favorite one most of the time and use the other one when need be. Once you learn one, learning the other is actually pretty easy. Octave is great for crunching numbers and can be used for many forms of scientific computing. However, I would probably only recommend learning it for data science if you're trying to get a job at a company that uses MATLAB. Julia is quite an ambitious project, and it shows great potential, but it's just too immature right now. It has a small community of active users compared to the more established languages, so it's often difficult at this point to find useful help on Stack Overflow and Google. Julia is all about speed. It wants to be like the C programming language for data scientists. So maybe if you watch this video 5 years from now, Julia will be the queen of machine learning languages. I think Scala is the best of the JVM family of languages. It's especially great if you use it as a purely functional programming language. However, there are few machine learning packages for Scala, so it's probably best used for data engineering tasks. PySpark and Spark in general have very few machine learning algorithms. For example, there are a vast number of algorithms in various Python packages to enable you to generate hundreds of different kinds of regression analyses. But currently, there are only a half dozen such algorithms in PySpark. The reason for this is because converting algorithms into parallel algorithms is rather difficult. Spark will improve as more algorithms are added in the future. But for now, I would recommend it only when your model training task takes an unreasonable amount of hours to complete when it's processed by a single machine. So, whichever option you choose for machine learning, make it an open source language.